Okay, time to get started. Okay, let's see. Let me mark that. Okay, so yeah, hope everybody had a good weekend. And here's what we were talking about last time. We were up here, I guess. So we were talking about physical examples of divergence and Gauss's divergence theorem. So real quick, I just want to talk about kind of summarize what we saw in those examples. So talking about the light bulb example, one of my favorite examples, because it so dramatically illustrates that the flux that you measure on the boundary, right? It doesn't come from the boundary, right? I mean, it's really, really clear that it's the light bulb itself, the bright spot, where the divergence is huge, right? That's where the flux is actually coming from, yeah.
Yeah, just a question about this. So
Yeah.
if we were to just calculate because divergence occurs at one point, right? And the flux
With
occurs.
divergence is, yeah, it's
So-
defined at one point at a time,
So
yeah.
if we got the divergence of just the center, would that be the same as the flux of?
No, so it's an integral, right? So flux is an integral of divergence,
Right.
right? So what you'd have to do is integrate divergence. Now the divergence is going to be zero all through, here and all through there. That's all zero divergence. So one thing if the divergence was a constant in the very, very small volume of where the light is actually emanating from, then you could multiply that divergence times that volume. The teeny tiny little volume, right? But ultimately, the simplest way to say it is it's a triple integral of divergence.
But if it's zero everywhere but the center?
No, but it's not. But it's not the center. It's a tiny little volume because light bulbs don't emerge. I mean, photon does not emerge from a single point. That's not physical. There is no light bulb in the world that does that, right? There's always, however small, a little bit of actual volume there. Does that make sense? Yeah, it's a really good question because we tend to oversimplify and think about, point masses and point sources of light and stuff like that, but it's just not the way the physical world works. Yeah, totally. Okay, so I love this example because it illustrates, I've been pitching to y'all for a long time now that stuff that you measure on the boundary doesn't actually happen there. That's just where you measure it, but it actually comes from the interior. And you probably get that when I'm talking about change in the fundamental theorem of calculus, and the derivative is showing where things are actually changing. Well, this really underscores it for flux, I think, really, really well. Flux really literally comes from the interior. Okay. Then we also talked about this. Oh, whoops, didn't finish erasing there. We also talked about this example where we have a gas. Initially imagine there's some sort of constant density gas, like a cloud or something, right? And then imagine that the temperature just starts to increase uniformly throughout the cloud. And of course, temperature increasing means that the volume increases, and that means that the gas starts to flow outward, right? And I claim, and I don't want to get bogged down in the details, but I claim that flow of gas would be something like this. Well, again, there's going to be flux, right? The flux that you measure on the boundary, that flux comes from the fact that there's gas that was inside of this sphere that is leaving the sphere, right? There's physical stuff that's in the process of leaving. Stuff that had been on the inside and will no longer be because it's expanded to the outside, right? So again, where does that come from? The fact that there is mass leaving the sphere through leaving the ball through this boundary sphere. Is that because the mass is the density is decreasing just on that boundary? No, the density is decreasing everywhere, right? The gas is expanding outward from the center, and all of the density is decreasing. So ultimately, the loss of mass, the loss of mass happens on the boundary, but where did the loss of mass actually come from? Well, it comes uniformly through, color change. It comes uniformly throughout the interior, as indicated again by the divergence. In this case, it tracks that the divergence that you compute here is in fact constant, as one would expect. Okay. Now, so with that summary, let me point out now the differences between these two examples. There are some big differences in the kinds of fluids that we're talking about here. So in this light bulb example, we're talking about a fluid that is generated. Right, there's a generated fluid here. There's no change in density. It's not like we're getting more and more photons collecting in one part of space, or photons that had been collected sort of waning and disappearing away. No. It's just this is a steady state deal. Photons are being generated. Photon density is not changing at all. Okay. By contrast, it's actually kind of the opposite with this example, where here we have nothing's being generated, like photons here. We had a finite amount of gas, and we're just talking about that same amount of gas, right? So on the other hand, the density is changing, right? So these are sort of complementary examples. In one case, the fluid flow is representing a creation of fluid. In the other case, the fluid flow represents a sort of a merely moving of fluid. Okay. All right. So with that difference in mind, here's the thing. Sometimes you have both. There are some physical scenarios where you have stuff is being generated or possibly destroyed. And furthermore, the density might be changing in various places also. Right. So an easy example of that would be to think about, sort of long-term population of, birds or something like that. Right. Those birds are easier to sort of imagine, I guess. But over the long term, if you measure over months and years and that kind of thing, and you're measuring, the bird population and, the movements, migration patterns, whatever it is of birds around some area. And you want to keep track of how the number of birds in a certain area is changing with respect to time. Where does that come from? What does that relate to? Well, there's several things. Birds are being born. They're having baby birds. That's where some of the birds are come from, right? So there is literally a generation of birds, and also some birds are dying. That's the opposite. That's a minus sign of generation, right? On the other hand, you can also have a changing quantity, right? So like in the gas example, the number of birds in an area can be decreasing. The number of birds in an area can be increasing. So when you measure flux in a situation like this, where both of these stories can happen, right? Then flux does not immediately tell you how fast birds are being generated, right? It also does not immediately tell you how the rate of change, total number of birds is changing, right? The flux is, it's complicated because there's these two separate terms that can contribute. So the purpose of this example is not that I want to actually address situations like this in this class, get into the weeds of particular examples. I just wanted to point out that there are these kinds of situations. And so certainly in any physical application of the divergence theorem and, thinking about vector fields and fluxes and that kind of thing, think through to yourself, wait a minute, are we looking at one of these deals, like with light bulbs? Or are we looking at one of these deals, like with the gas where the temperature is increasing? Or are we looking at one of these deals where it's both? And so you have to interpret appropriate to the example that you're actually dealing with. So, the purpose of this discussion here is just kind of a heads up. Okay. All righty. The next example I want to talk about is gravitational fields. There's some really good reasons to study gravitational fields. One of the big ones is going to be the next example we're going to talk about, which is electric fields. And I'll talk about the connection between electricity and gravity in just a minute. For the moment, let's just focus on gravitational fields. What I like about gravitational fields is that they're relatable. Right? I mean, we experience gravitational fields every day. And we also kind of know that, when you go up in space, This gravity is weaker. The further you get from the center of the Earth, the less gravity there is, right? You go to the moon, there's a lot less gravity there. So people have a kind of a good sense and intuition for gravitational fields that are kind of like this. Of course, the arrows go the other way. You'll see why the arrows point outward in just a moment here. But the point is they're stronger when you're closer and they're weaker when you're farther away. And they're always radial. Okay. All right. So to talk about gravitational fields, first thing I want to point out is the formula for the point mass gravitational field is this. Y'all have probably seen this in some form or another anyway, in a high school physics class. If you haven't, don't worry about it. The big thing to note about this, and real quick aside, this is for a point mass, which is not real world like we were just talking about, right? So this is a non-physical thing. There aren't actual point masses. Masses are always distributed over volume in the physical world. But as a mathematical sort of, approximation and shorthand, this is very convenient. Okay, so in this hypothetical point mass gravitational field, the things to notice are it's radial and it is inverse square to the distance. Okay. All right, so this is, let's put inverse square radial. And the thing is, so is the flow field for a point light source. If you go back up here and look at this vector field here, where we have again, physically implausible, but good approximation. Imagine a single point light source. It would be inverse square radial. So, okay. This physical metaphor then of, in this case, we have photons emanating outward, right? That's what light is. You can physically kind of, just for imagination purposes, you can visualize that that's what's going on with gravity, that's how gravity gets communicated. And there is, I will confess, I'm not sure on the current state of affairs of the view of the actual physicality of this, but they talk about these things called gravitons that are to be thought of as like little photons, except gravitons communicate gravitational force. That's where gravitational force that's how I, sitting up here, not physically touching the center of the Earth, right? That's how my physical body is communicated that, oh, hey, you know what? Force downward, right? It's because I keep getting hit by gravitons that are being shot out by the Earth. So the more gravitons that hit you, the more force of gravity pulls you toward it. But anyway, that's the I'm going to say theory. I don't necessarily mean that anyone physically believes that, but I'm not sure also that they don't. But we don't care in a math class at all about whether that's physically, real or not. What we care about is a perfectly good model, and it is entirely representative of the equations of how gravity works. So I think this is a great way to think about gravity, and I hope you'll, kind of adopt it, that this is, what gravitational fields are. Even though maybe not, I don't know about the physicality, again, don't care, but think of gravitational fields as being flow fields of not photons, but gravitons. Okay, all right. So that in mind, let me write down some equations here. And for the moment, we're going to start with this equation here. And I'm going to, again, for the moment, I can't see. Again, for the moment, I'm going to scratch off this negative 4 pi g. I'll come back to that in a second. Let's just start off by looking at just this by itself. And this equation I have in purple, edited as I have it, is familiar. Mass is triple integral of density. All right. No problem. Now I'm allowed to multiply both sides of an equation by a constant, perfectly legal, right? But still, morally, this is still saying mass is triple integral of density. Okay. Well, here's the thing. With this idea that gravity is communicated by gravitons, right? With that in mind, this starts to make a lot of sense right here. The particulars of the constant we don't need to worry about, but if mass creates if mass generates and spews gravitons, then, well, if you have mass inside of a surface, then that mass is where the flux of gravitons through the boundary comes from, right? And more mass makes more gravitons. How many of those gravitons are going to go through the surface? Well, all of them, right? So the more mass you have on the inside, the more graviton fluid flow flux, right, you'll have on the boundary, because again, mass creates the gravitons, and all of the gravitons eventually have to leave the surface. So again, I think this is a very physically relatable equation, and this constant here is details and units and stuff like that. That is, again, somebody else's problem. Okay, so I think this is believable. So again, this is pretty straightforward, and this is pretty believable. And then, of course, this is just the divergence theorem right here, right? So what we in effect have then is an argument for this equation right here that measures, that's a way of thinking of the divergence of the gravitational field. If you have a distribution of mass, that distribution of mass creates a gravitational field, and you want to know what the divergence of that gravitational field is, well, it's a well-known constant multiple of the mass density. And again, the argument, two ways you can think about this. One is to sort of connect the dots through like that. Another way to think about this is, well, divergence represents how much of the fluid flowing around is actually coming from a given area. Well, why would there be any fluid coming from anywhere? Well, fluid comes from mass. And if you want to know the flux density, wouldn't it stand to reason that it would relate to the mass density? Pretty plausible. So view that whichever way you like. Okay. I've thrown a tremendous amount of ideas at y'all in the last, what's that been, 10 minutes or whatever. Does anyone have any questions about any of that? Everybody on board, kind of buy it? Okay. All right, so I made the claim at the very beginning here that gravitational fields are a good segue into electric fields, and I've explained what the connection is. And well, the connection is actually pretty easy, but it's not physical. I'm not saying that gravity is ultimately an electric field or the electricity is ultimately, no, they're completely independent forces, right? But the thing is, gravitational fields being inverse square radial, as we see here, well, guess what? So are electric fields. It's just the equation. It's just, that's just, conveniently the physical universe has these two separate forces that are just so similar to each other. Now, of course, electric fields don't come from mass, they come from charge, which is a different physical quantity and less relatable. And that's why I like to do electric fields second. Electric fields are so physically unrelatable that we didn't even know they existed until a couple hundred years ago. Right? So subtle, right? Easy to miss, and not sort of everyday sort of radial. So I like the idea of introducing the ideas that I just introduced first in the context of gravitational fields, where it's physical and relatable and visceral. And once you feel like you get a sense for how that works, then, oh yeah, electric fields, same deal. So you'll notice that now here, instead of, let's see here, you know what, let me do it like this. Instead of mass being a triple integral of density, here we have charge being a triple integral of charge density. And it's exactly what it sounds like. It's charge per unit volume. No, but still, quantity is a triple integral of a density is, highly believable. It's the kind of thing we talked about a lot. And the claim here, and then this is it's not really so much a physical thing, but this is just this is Maxwell's first equation. This is a version anyway of Maxwell's first equation, is that charge is what creates electric flux. In the same way that mass, you can think of mass as just spewing out gravitons, you can kind of think of charge as spewing out some sort of particle that communicates the electric field, and you're going to have this urge to call them electrons, but that word's already been used for something else, so you can't. Right? But as if charge emanates some sort of a fluid that communicates electric forces, in which case the more charge you have, well, then the more flux there is of that fluid, because, well, it's all got to leave your surface eventually. So same arguments. Note that that therefore then gives you this equation here, and we call this also Maxwell's first equation, just like we did this one. Maxwell's first equation, because they're both saying, I mean, morally the same thing. Flux comes from charge. That's what this is saying. And this is saying flux density comes from charge density. So, I mean, it's the density version that says exactly the same thing as the other one does. So that's why we don't make a distinction. This is not Maxwell 1 and 2. This is Maxwell 1 and Maxwell 1, alternate version. And they call them the one on the left, the integral form, and they call the one on the right, the differential form. Anyway, that's what that says. So again, it's just think about gravity and gravitons and light bulbs, and this is all the same stuff, different physics. Okay, what do you think? Again, reminder, this is not a physics class. I'm not interested in whether you know physics, right? I am, however, though, interested in whether you know the math behind what's helping us understand the physics here. So in that this is an application of the divergence theorem, and an example of the divergence theorem in action. That's the part that I want to make sure everybody understands. And whether you remember this constant, I don't really care. It's easy to remember, but the point is that's not the point. Okay. Cool. Let's move it along. So last theorem, called Stokes' theorem. Side note, just for fun, I'll point out there's a lot of discussion as to the proper spelling here, as to whether there is an S here or not. Different books make different choices, and it's a grammar question. It's not a math question at all, right? But I looked into it. I'm going to say carefully, somewhat. When I was writing my book on the subject, I want to get it right? And so I looked up, do you or do you not put the S after the end of the apostrophe in the possessive of a name that ends in an S? And I got some pretty mixed reviews. And if you look at grammatical authorities, I was not able to identify a uniformly held, crisp, simple answer to that question. And in fact, different math textbooks make different choices on this. So I think that's hilarious. I grew up calling it Stokes's, where there's the kind of the double S pronounced. And so this is the one that I gravitate toward myself. But anyway, you will also see it as just, Stokes theorem. Okay, but do be aware, and this one is super gauche, make sure you don't do that. Stoke was absolutely, unambiguously not his name, right? So that one is not an option. Okay, all right, enough of that. Okay, so Stokes' theorem, it's a lot like Green's theorem. It's a lot like the divergence theorem. It's a lot like a fundamental theorem of line integrals. It's a lot like all these theorems that we've been talking about that have, some discussion of boundary and some discussion of an accumulating quantity and an ensuing interpretation of density. So you're going to notice the pattern here. And I get when I write these notes, I try to do so in such a way as to follow a pattern to help you see and notice the pattern. So different geometric details, of course, but same rough pattern. So the very first thing we need to do is to talk about surfaces in space. And what do we mean by the boundary of a surface in space? Okay. So casually speaking, boundary means, I'm going to say loosely speaking, exactly what you mean, exactly what you think it means. It's the edge. It's where you get the paper cut from, right? It's where if there were an ant walking around on the surface, where the ant would get confused. Hey, what's going on here? Where to go? Where things start to seem weird to the ant. Anywhere else on the surface in the middle, he's just walking along, oblivious to there being anything going on. Okay, so do keep in mind though, just like with Green's theorem, just like with the divergence theorem, boundary is now a loaded word. Boundary means oriented. This word is an oriented word, right? And so when you see boundary of a surface, knee-jerk reaction, you should instantly think, okay, there's an orientation. He said boundary. Boundary means an oriented. Which boundary? Which orientation on this boundary is the correct orientation? So again, there's a convention. Again, it's arbitrary, but it's highly conventional. So it's not optional. It is arbitrary, but it's not optional. Highly conventional. The choice goes like this. If you have an oriented surface, and now keep in mind, we're talking about an oriented surface, and oriented surfaces have a normal vector. So there's my oriented surface. Got a surface, got the normal vector, whichever way that might happen to point, whatever. The boundary then is, of course, again, it's where the ant gets confused. It's where you get your paper cut. Which is the correct orientation on that boundary curve? The answer is it's kind of a weird little geometric story, but you have to use your right hand. As usual, mathematicians favor right hand. That's what it is. But point your thumb in the direction of the surface orientation. Keep in mind that surface orientation is the normal vector. So point your thumb in the direction of the normal vector. Right hand, again, very critical, right hand. So thumb in the direction of the normal vector. Notice your fingers want to bend around in a particular direction, and your fingers define what I loosely like to call a swirl. So that swirl in this case, kind of like that. So you just got to, figure, just kind of do the little physical gesture and persuade yourself there's the swirl. 2 seconds. Let me just finish the story. That swirl will sideswipe up against the boundary in the correct direction. And so that gives us this direction as the orientation for the boundary. Yeah, go ahead.
So I was just trying to understand what we're talking about here in with Stokes Theorem. So here we're talking about a curve.
Oh, yeah.
So the curve is
yes.
bounding the surface.
Yes, that's right. So we have a
sheet of paper.
That's right. We have a surface and a boundary curve. The divergence theorem is about a three-dimensional solid and a boundary surface.
So the surface is
encloses
an entire thing. So like
solid.
an egg or like a donut.
Sure.
It would be like the outside.
Sure. Exactly.
Okay.
Yep. So it's dimensionally different, and there's a surface in both stories. But yeah, that's right. But
one of them is like closed.
And with Gauss, the surface is the boundary. With Stokes, you're looking at the boundary of the surface.
So then what is a closed surface?
Closed surface is a surface that is a boundary. It's a surface that doesn't have an edge because it closes up. So yeah, therefore is a boundary of something.
Like a sphere.
A sphere is a closed surface. That's right. Yep. Yes.
So this Stokes theorem, is this just giving us, it's just telling us like the direction of tangent?
Yeah, that's right. All I'm doing so far is telling you what this word boundary means. And so we haven't gotten to Stokes's theorem yet. The theorem comes later. Right,
But
so-
then it's just like the squirrel side swipes.
Yep.
That's just like the tangent line. at that
Yeah,
point.
that's right. That's right. That's right. So that's right. So the way we communicate with an oriented curve, the orientation of a curve is defined, you're right, by the unit tangent vector. So the unit tangent vector is the one that's implied by this side swipe. Yep. Okay. So for whatever it's worth, I mean, this is the most what's the word here? Geometrically confusing, hardest to put into action convention for boundaries. And of course, we've seen, boundary, like the boundary in of a two-dimensional region in R2, right? And there was a fairly simple rule there, and it's on your left, but I mean, most of the time it's counterclockwise, and so it's just a rule to remember. You just got to think it through. Here, you really have kind of a geometry problem, right? Or relating a surface orientation to a boundary curve orientation. And it itself is kind of a weird thing. Now, I will point out there are different ways to describe this same rule. I've given you what I think is the most geometrically satisfying answer. There are different versions of this. For example, another way to describe ultimately the same answer is that if you have a normal vector for your surface, there's your normal vector. Imagine that normal vector is telling you how we've got a little person here. That's telling you which way that person is standing on your surface. And now imagine this person standing on your surface, then standing on the boundary accordingly, and then walking along the boundary. Right? So which way should he walk along the boundary, you might ask? And the answer is this person should walk along the boundary such that the region is on his left. So if you want to notice that gives us the same answer, right? That still gives us this direction that he should walk in order for the region to be on his left. So if you want to think about it that way, you can. The problem with that point of view is that sometimes, what if your surface is oriented downward? What if this is your surface like this, right? Surface is oriented downward, and now you're thinking about the boundary curve and which way this person is now upside down and he's walking along the boundary, right? And so which way is his left? And you're going to find yourself needing to, and then, you can kind of straighten it out, but you have to, there's a perspective awkwardness there. Whereas it's really easy to just turn your thumb upside down and then note that your fingers curl the other way. I think this is much easier than these alternatives that you could do instead. Everybody see what I mean? So that's why I push this one. Okie dokie. So that's what boundary means. All right. Again, there is a notion of accumulation. This is not going to shock anyone, I'll bet, but the accumulating quantity is boundary circulation, right? We've seen Green's theorem. In Green's theorem, when you have, it's not a surface, but it's a two-dimensional region, but a two-dimensional region's the surface is a two-dimensional. This kind of seems a lot like Green's theorem's context, sort of. It's just that now we're floating up in space, but still with Green's theorem, we looked at little pieces of area and we looked at their boundary, and it was boundary circulation. That was our accumulating quantity. So same thing here. It's just that now boundary circulation is around the boundary of a piece of surface, and it's floating up in space. Still circulation. Is that cool? All right. The cancellation that shows that this actually accumulates is the same story that we've seen before. you have this edge in common between these two pieces. And as part of the boundary of that surface, we're going that way. And as part of the boundary of this piece of surface, we're going that way. And same edge, opposite orientations, they cancel. That cancellation is what makes the accumulation sort of work out. I mean, I'm being real quick about this because it's exactly the same point as we made with Green's theorem. And it's morally pretty much the same point as the argument we made for the divergence theorem and the two-dimensional divergence theorem, right? So arguably this is our fourth time making this case here. So punchline though, boundary circulation accumulates. All right. Okay, and yeah, so you know what? Let's I'm going to take my own advice here, and let's go back and look at the analogous picture from section 6.2. Which I have so this is Green's theorem, right? So this is a discussion we had here, and we had this picture and shared edge. Whoops, that wasn't the color I wanted. Here we go. Shared edge. As part of this piece, we're going that way. As part of the boundary of this piece, we're going that way. Same edge, opposite orientations, they cancel and thus accumulate. It's the exact same thing. It's just that this is lying flat in space, and this is happening suspended up in space. Okay. Okay. All right, and so as every other observation we've made, and again, let me be really quick about this, you know, that means that circulation, this is, now that we know it's an accumulating quantity, we can treat it like it's a kind of stuff, like it's kind of like mass, kind of a, you know, it's a physical concrete kind of substance or something. So in particular then, even though we're talking about boundary circulation, and so we measure it on the boundary, nevertheless, this is a stuff. And so it's actually happening in the interior. And so you want to, you know, keep that in mind as we go along. Okay. So again, there's a density story. Again, now that we can talk about circulation as something that happens locally. Here's a picture of a little bitty piece of surface. I can talk about the circulation on that piece of, the boundary circulation around that that piece of surface. That boundary circulation per unit area, right? In other words, what do I multiply by area there to get circulation? Well, this has this associated density to it, and do this in blue. So circulation per unit area, the thing you multiply by area to get circulation. How much circulation is happening locally per unit size? Well, there's a formula, and this is what the answer ends up being. This is a little bit disappointing. It's a lot of students would have looked at this and seen patterns and kind of maybe suspected the answer would be curl, and that's not quite right. Orientation matters, and I'm going to expand on this on the next page. But for the moment, I just, you know, we're inches away from a theorem. I want to run it into the end zone and spike the football, and then we'll go back and we'll talk about this issue with, you know, what's the deal with the end there, right? But anyway, for the moment, let me just say, you know, it depends on how your piece of surface is oriented, and we will come back and talk about that in a second. But anyway, this is the big point. Circulation density is curl dot n, and yeah, again, details to follow. Okay, so let's run it into the end zone real quick. We have, I mean, y'all recognize this layout here. This is the same. This is how we ran it into the end zone with Green's theorem. After which, I pointed out, hey, you know what? You could run it into the end zone the exact same way with the fundamental theorem of calculus and the fundamental theorem of line integrals, and then the two-dimensional Green's theorem, and then finally the three-dimensional divergence theorem. So arguably our sixth time now to see this little story, but we've got this quantity, circulation. we observe that that quantity accumulates. We have a corresponding notion of density, and that gives us a theorem that altogether then, this line integral is that surface integral. And then, of course, a lot of people will notice, and I'm a big fan of the following myself, that that the dot in the that's in the integrand there, well, that in fits very nicely with the ds that we have on the outside to make this our familiar ds vector. And so slick move, and I'm a big fan, and I hope y'all will all do the same thing here. But this is really kind of a better way to write that integral. Certainly it's a shorter way, more compact. And so anyway, you know, take your pick. They're both right. Either is fine, but I like the latter. So here you go. There's Stokes's curl theorem. And note now, if in case it might be somewhat satisfying, now curl is our integrand. And that's another reason that it makes this look satisfying. Yep.
Were you saying before that it wasn't curl?
I'm saying curl isn't the density. Yeah, but it is here the integrand. Yeah, so that's right. So if you want to use the word density, you know, circulation density, then yeah, there's a dot in that you have to deal with. Yep. Well, and again, I'm going to come back in just a minute and talk about the details there. Yeah. Okay, so let's see an example of this in action. Neat fact, as usual, if you find yourself looking at one kind of an integral, this allows you to turn it instead into a totally different kind of integral, and sometimes that's really useful. Right? So here is such an example. Suppose we want to compute a line integral, and I've got a vector field given, and I've got a curve given. In fact, the curve is given parameterized. And by the way, here's a landmine. Let me show you this landmine here. You see this question as written. Because the curve is given parameterized, you're going to feel a temptation and urge to compute it from the parameterization, just from the way the question's given to you, right? And notice there's nothing in the way this question is stated that says you have to parameterize or that you have to compute from parameterization. So, you know, don't take implicit you know, cues just from the, you know, the parameterization happens to be given. That does not mean that it's going to be the best way to solve a problem. And in fact, of course, in this case, it'd be a nightmare, right? Because again, we've noticed this before, but that's telling me X and Y. And so all of this X and Y nonsense, everywhere you see an X and a Y, such as there, and there, all that's going to be trig. And then, you know, look at this is, I've seen worse, but still I've seen better, right? That doesn't look like a fun calculation. So let's not fall into the trap of thinking you have to do it that way. All right, so here's what we're going to do instead. We're going to notice instead that our curve that we were given, that parameterization right there, and here it is. It's the unit circle in the XY plane. But importantly though, oriented as I've got drawn there, that curve is a boundary. Right, and that's a big observation. When your curve is a boundary, keep in mind that's what Stokes's curl theorem says. And again, this is the big catch with Stokes's theorem is Stokes's theorem does not say this will. Here's a way to compute any line integral you might feel like. No, it specifically says right there. This is for computing line integrals around boundary curves. Right, so we have a boundary curve. This is a boundary. And so I know that I can use Stokes's theorem. Does everybody see that that first observation there? Yeah. Mm-hmm. Yeah, I haven't gotten to that yet. Yeah, I'm going to totally talk about that. Yep. Right. Okay, so let's talk about orientations then. So this surface is a boundary. It's a closed curve, you know, right? So how do I know that this is, or excuse me, how do I know what the orientation is? Well, this is this business here, right? We have rules for what the relationship is between an oriented surface and an oriented boundary curve. It's this rule right here. Right. And so, okay, well, we've just got to apply that here. Now we have to kind of apply the rule backwards here, because rather than having a surface orientation given and then, finding the induced boundary orientation, I have the induced boundary orientation given, and I have to reverse engineer which way is the orientation of the surface. So it's trial and error. And of course, there's only two things to try. And just to keep it interesting, I don't want to discover the right answer with my first try here. But let's think about if this were oriented upward, hypothetically, could this be right? Is this going to induce the orientation the right way? Well, let's see here. If my orientation were upward, my thumb here makes my right hand fingers go this way, and that induces this swirl, and that swirl is just going the wrong way. So this is a trial and error. I entertained the possibility this might be oriented upward, and I see that it can't be. Yes.
How do you know the direction of the swirl?
Right hand. So normal vector, thumb in the direction of the.
I mean, like, how do you know that it's moving up? Or how do you know which way it's supposed to
Oh,
go?
how did I know the purple orientation that's given? Well, because that's the orientation. The curve is given parameterized like that, and parameterizations imply an orientation. Right? When you have a parameterization, the orientation of the parameterization is, well, whichever direction that curve is actually going. And so this is a going back to chapter 6 business. But when you have a parameterization, take the velocity vector. You can think of it in several different ways. In this case, I think I would probably look at this and say, this is a reflection of my usual unit circle. And when you reflect, something going that way, when you reflect it, well, then it's going the other way. Does that make sense? Yeah. So either way you like, but the short answer to your question is the orientation that we're aiming for, this boundary orientation we're aiming for, is implied by the parameterization. Okay. So we're 0 for 1 on orientations. Let's try the other possibility now, right? So again, looking at this surface, the other possibility we're going to entertain is that maybe the normal vector goes that way. Could it be? Okay, well, thumb in that direction, and look at my fingers. And again, you got to do this for yourself, right? But your fingers go like that, and then that means that the swirl is going like that, and that tracks, right? That's what it's supposed to do. That gives me the correct orientation. So that means that this is the correct orientation for my surface. Is everybody on board? Arguably, this is the hardest part of the problem because of it's so visual and geometric, and Okay. And again, so therefore, correspondingly, big points, right, on an exam. So if you use Stokes' theorem, think very carefully about how you're going to interpret the orientation of your new surface, your anti-boundary surface, right? And furthermore, give some indication, even if it's just kind of figures, but of what your thought process is about where you got your orientation from. Okay. All right. But anyway, there it is. And with that said, it's all over with the shouting, really. So our curve is a boundary. Boundary circulations are fluxes of curl. And it's just kind of a matter of writing stuff down here. Let's see. We have, here's our vector field. That's the vector field of which you need to compute the curl. And if you compute that curl, you get 0, 0, 2. That's algebra. I'll let y'all do that. Make sure you can do that, right? Computation of curl, a bunch of little details in there. The normal vector we just got through talking about, that normal vector, 0, 0, -1. And like I say, all over with the shouting, because I have a really easy integral here. That's just an integral of a constant over a well-known surface. And so you can make an area argument, and there's your answer. What do you think? Everybody happy? Okay. We are out of time, so this is a pretty good place to draw the line. Draw it right there. I did say that I would, soon be talking about the density business, and so that soon will be soon. It'll be first thing on a Wednesday. But anyway, so that'll be our next thing. All right, y'all have a good day. See you later.
I have a quick question.
Yep.
How did you, so I understand how we talked about the direction of it, but how did you get to the actual numbers?
For the what now?
For the normal, 0, 0, 1.
Oh, well, yeah. No, I got you. Because my surface here is clearly sitting inside of the XY plane. And that means that the normal vector is either straight up or straight down, right? And nope. That's every geometric aspect of every example is peculiar to that example. So here I'm using what I got. I've got tools in my toolbox and I'm using them. Yep. So yeah, in different contexts it might be harder. If you've got like a paraboloid or something, then finding this might not be particularly convenient. In which case, what you would do is you would say NDS is capital N ds dt and parameterize your surface. Correct. This whole thing here just wouldn't work. That's right. Yep. Okay. Yeah. Let's see. Those. Oh, I've got to stop the recording. Super quick. Stop. There we go. Bye.